you can say it right now. Thank you.
All right, thank you. So thank you very much, everybody, for coming. Let me take a few minutes to introduce our today's speaker. Today's speaker is Jakob Zeitler, who is a PhD candidate in computer science at UCL. He does great work in the areas of causal inference and machine learning, in application to causal inference. He's not new to Exeter. Way back in 2017, he became an alum of this great university. And now he has came back to basically talk about his more recent work in the partial causal application. But this I'm gonna hand over to you, Jacob.
Yeah, thank you, guys. I think we're gonna just head straight in then. So my name is Jacob, as you just heard. And today I'm gonna present to you on partial identification and some recent advances in the field. And just a hands up, who has heard of causal inference before? Yeah, that's good. And then partial identification. Okay, nice. So this is a talk for you then. So we can all learn something. So this is based on two recent papers. So this is my first author paper. The majority of the talk will focus on that in the later part. And this is another one I'm going to mention here. So when you have the slides later, you just click on the links and follow up with that. We're going to have a three-part structure. We're going to look at some background plus inference, so we're all on the same page. And then we'll look at partial identification as the key, meaty part of the talk, where we look at why we do it, the challenges, some solutions, some alternative methods, and then we'll end with a Q&A. We can do questions during the talk for clarifications, bigger one as well, if you feel like doing big questions. But if you have like a really big question, then we'll probably do that. So, causal inference, why does it matter? Here's a graph that's pretty popular. It comes up once a year when people get the Nobel Prizes. And so we see the chocolate consumption on the x-axis and then the Nobel laureates per million population. And we can see there's probably a really nice correlation here. In fact, it's a statistically significant correlation. But of course, correlation, what can we learn from it? So does it imply that chocolate consumption causes Nobel laureates? So of course, I think everyone agrees. Absolutely not, because correlation does not imply causation. So how do we figure out then causal questions? Let's take a look at another example here. So this is, let's say a simulated gene knockout experiment. So in gene knockout experiments, you take a gene and you set it all the way to 0. So the activity of the gene is at 0. And then the phenotype, so the expression of the gene, for example, the height of the organism, that one might be affected by it or maybe not. So that is the question we have. So how could we predict the level of the phenotype based on the activity of the gene? And just looking at this data here, it could be probably anywhere around the red line here. Now, if you actually have some knowledge about the structure of the gene network and the phenotypes, and if we know that gene IA directly influence the phenotype, then we could probably say, well, this looks pretty nice cluster. We'll probably just get a line through here. And if we set the gene A to 0, which is a gene knockout, then the phenotype is probably going to be somewhere here as well. And that's a scenario we can imagine. Let's take a look at another scenario here. So scenario 2, something called gene B. Again, we have some activity in phenotype data, but this time we look at a different structure of the world. So this time we assume that there is another factor that causes both gene B and the phenotype. And in that case, well, if gene B is changed or knocked out from here, then we can actually say that it's going to be in that range here, because everything we know about gene B and the phenotype right now is that the phenotype has been observed in this range, and the gene B doesn't actually impact it. So these are two different scenarios, two different causal data generating processes. So why is that relevant? Well, when you ask causal questions, you're interested in the causal effect of an intervention. So for example, I want to change the gene. What does it impact on the phenotype? And the core question usually there is identifiability. So that is a key term you'll find on page 3 of every causal inference book. And so the question there you ask is, can I express the effect of interest as a function of the observable data? And there's only two answers. So either yes, you can do that, in which case you say it's identifiable, or no, you cannot do that, in which case it's not identifiable. So what that as a function of the observable data means, we'll see in a second. And so we'll see that with the example of confounding. So confounding is generally the bad guy in causal inference. That's what you want to avoid, or that's what you want to adjust for. So if you have confounding and you know what it looks like, you can actually adjust for it. That's called backdoor adjustment. Look at some scenarios here again. So scenario one, no confounding. You can represent it with a graph structure like this. You have a variable x that influences y. And then if you ask the question of, if I intervene on x and change it here up and down, how does it influence y? Well, if the world looks like this, then it's simply a joint distribution here. So whenever you change x and you have the conditional distribution of y given x, then it is just factually that value. So that's the math part, which we're not going to get too much into here, because what's more important is the scenario two, which is the confounding scenario. In that case, we have a variable here on top, again, kind of the bad guy. But in this case, it's actually not so bad, because if we do know what C is, and we can observe it and measure it, then we can use the backdoor adjustment formula, which is down here. Again, very fundamental, and you can find that in any causal inference book as well. So in that case, you just take the conditional probability of y, conditional x and c, and then you weight for the probability of c. Just plug it in, and you're good to go, and you have an unbiased effect estimate. You have the, for example, effect estimate of gene A knockouts on the phenotype. All right, so basic causal inference here, confounding bad guys. Let's think of another variable W. So W here is another confounder. Would that be a problem? No, it's not a problem, because we can just plug in W together with Z into the backdoor formula, and it's still all fine because we've measured all the confounding. Now, W is latent. Is that a problem? So I put here these dashed lines around it, which people use to indicate that we can't measure it. So we might know that W exists, but we just don't have the data on it. We can measure it. Is that a problem? I see nodding and shaking heads. But in my opinion, it is a problem. And so, and I don't think it's just my opinion, but basically this is called as a violation of the no unmeasured confounding assumption. So no unmeasured confounding means that we have measured all the confounders here. But of course, if W isn't measured, then this assumption is violated. If it's violated, then we can adjust for W. If we can't adjust for W, our effect estimate is going to be biased. Not good. If you're dealing with patients and you just estimated a wrong amount of IV fluid, the patient could take damage from it. So this is basically the problem of confounding. If you have confounding, but you can't measure it, you're violating a crucial assumption of causal assumption of observational causal inference. And so that is going to be a problem for you. So let's sum that up here. The morale of the story is assumptions are essential for identification. If you have a causal quantity you're interested in and you want to calculate it, you need to identify it. If you can't identify it, you're going to get biased effects. And causal inference is essentially a language to express your causal assumptions, to encode your causal assumptions about the world. And it's just the fact that if you're not putting any causes in your models, you're not going to get any causal answers out of it as well. So here's a link to Nancy Cartwright, a philosopher that elaborates a lot more. But this is often a mantra that's a phrase that's used in causal. Okay, that was the setting here. Now we're hopefully all on the same page. Now we can ask the question, partial identification. Why are we doing it? Why is it relevant? Well, if there's no identification in causal inference, then what are we going to do? And so there could be several reasons why there's no identification. Maybe you decide that you don't want to go for identification because you just think it's such a strong assumption. So the W that wasn't measured, you could say, I can't measure it. Any calculation I make is not going to be useful. It's going to be biased. Or maybe you also have just a model for calculating your causal effect of interest, for example, the gene knockout impact. But you also want to compare it with models that have weak assumptions and see if your strong model agrees or disagrees with the weak model. And so that is where bounding of effects comes into the game. And so instead of having this backdoor identification strategy where you just have this formula, you plug in your confounders and you get that random number, so it's just a random number here as an example. We're going to try to get some bounds on it instead. So that's a lower bound here and an upper bound. And the true effect is going to be in the middle here. So it could be a lower bound of 0.1 and an upper bound of 0.4. And if the true effect was 0.34, it would be here in the middle. And it wouldn't be a scalar or a number that you can give to a doctor or something. But at least in this case, for example, you could say that it's a positive effect because the lower bound is above 0, the upper bound is above 0. So the effect is at least positive. So it's a less informative method, but it's more robust, as we'll see, because it makes less assumptions. So, summing it all up, there are 3 points. Number 1, causal inference is all about assumptions. Number 2, if we assume a certain causal structure, we can take, for example, the backdoor adjustment and achieve full identification of the effect. And number 3, if we don't want to make these strong assumptions for causal inference, then we can still go for something called partial identification. So that's the setup. Any questions on that? Yes.
When it comes to the confounders that I'm not aware of, like, is there a way to tell that I've caught all the confounders that matter? Like, because it could be that you just don't know what you don't know.
So strictly speaking, no. That's why it's called a empirically unverifiable assumption. So there's no way in this life or this existence that you could measure or test whether you've missed one. Practically, what you do is you go and talk to experts and you're like, okay, this drug, what is it affected by? Do I have age? Is it people's socioeconomic status? All these questions. And there's a movement, for example, just take anything you can measure and throw it in there and then say, well, if we've measured everything we could measure, that's as close as we can get. But practically speaking, it's still in a bit of a hazard zone because there could be one more factor that changes a positive effect. So it's a very crucial point about this.
Not sure that's the right time to ask this question, so please feel free to ignore it and answer the other if you feel it's better. So the last time I looked at the causal inference literature was about 10 years ago, and at that time there were 2 strong schools in the literature. One, Donald Rubin with Don Rubin even model, and economists, and with the invents and local average treatment effects. And from my impression that I built 10 years ago, they wouldn't like this approach, right? With those, unverifiable. Obviously, there are assumptions that, and there was Judea Perl with do calculus that you're using. My impression, and I haven't been following the literature in the past 10 years, was that the 2 schools have become sort of closer together. And there are some economists now using the do calculus. I'm getting interested in this, and there have been some attempts to rewrite the Rubin's framework using the do calculus. So, with this partial identification literature, where does it stand in this debate?
Yeah, it's a good question. So the short answer is they actually, both the potential outcomes and the Perl graphical models, they wrote about this about the same time, the same thing. So with potential outcomes and the graphical models, you can describe the same thing. Today, I'm using graphical models to explain it. I can also spend another half an hour and explain it all again with potential outcomes. And in a sense, they are merging. And so there's also papers that show that these schools of thoughts are interchangeable. I think, strictly speaking, graphical models have one advantage in terms of expressing your false assumptions. So they're a bit more strict, but in general, that is not a problem. But I think that is something we can definitely talk about after the talk. And I have a slide for that as well. But in terms of the talk today, we're going to focus on graphical models, tag like these Judea Perl, DAX, direct acyclic graphs. And I'm going to explain partial identification with DAX. But the paper that started partial identification in 1989 actually was a potential. So the very first kind of published formulation was a potential. But from my perspective, they're interchangeable. I think that's true. I happily be challenged. But otherwise, I think we'll move on with the partial identification story now. And we come back to that. It's a great question. Okay, so we're going to use the instrumental variable model to explain partial identification. So who has heard of the IB model before? Definitely economists. Yes, yeah, as well. Okay, so this is really useful. If you understand this, you can even get a job in London at a bank. So this is very, very fundamental. Today, we're just gonna use it to explain partial identification. So here's the story, right? You have a headache and you go to your doctor and you ask for treatment. So here, this instrumental variable model would describe that process. So we have the treatment assignment, the treatment reception, and the observed response. The treatment assignment would be the doctor. You say, hey, Mr. Doctor, should I, do something about it? And the doctor can say either, take aspirin or don't take aspirin. So we're going to assume this is a binary model. So each variable you can only edit either be 0 or either be 1. There's no loss of generality. And so the doctor says either 0 or 1, and then you go home and then you actually take the aspirin or not. So maybe the doctor says you should take it, and then you go home and you forgot about it. Oh, now your D variable is at 0. And then the next day you wake up and then maybe your headache is gone. So that's 1. Y equals 1, or your headache is still there, so Y equals 0. So the headache hasn't been there. That's the instrumental variable model. Now, as you can see, I didn't cover another variable here, which would be latent factors, which are a problem, right? We just saw that confound is bad. Confounds need to be adjusted for. So here I've indicated with the red one here. And so latent is another word for hidden or unmeasured. And so again, if you were going to use that model to calculate the effect of aspirin on my headache, then we would get a biased effect estimate. So again, the assumption of no unmeasured confounding is violated. And we can measure U, we cannot adjust for it, and the bias effect estimate is yielded by the model. So this is where we then introduce response function variables. So this is the crucial idea about partial identification. It's a very simple idea in my opinion, and I hope I can make that clear as well. So we're going to transform this graph. We can transform this graph into this graph here without loss of generality as well, I guess. And so each of these observable variables, Z, D, and Y, they're going to receive a parent variable called RZ for response Z, RD for response D, and Y. And we're going to see what these numbers in here mean. So we see here there's 2 numbers, here's 4, and here's 4. Let's take a look. Here's your doctor. And here's your response function variable, which is a parent of D. And this variable indicates all possible behaviors of yourself to the prescription of the doctor. So as a first one, we could have an always taker. That's a person that always takes aspirin, regardless of what the doctor says. That's a possible response, right? Then in the contrary, we're also going to have never takers. So if RD was equal 1, the variable D would always be 0, regardless of what the doctor says. That's someone who doesn't like drugs or forgets about it all the time. Then we're going to have compliers. So that's people that actually listen to the doctor. And so they're going to not take aspirin when Z is 0, and they're going to take aspirin when Z is 1. So who's missing after that? The fires. So these guys, they will do always the opposite of what the doctor is saying. So if they get the prescription for aspirin, they will definitely not take it. And if they get no prescription, they will definitely take it. And if you look at that, these 4 functions here, in a way, they represent all possible sets of behaviors of yourself to your prescription of the doctor. There's nothing else you could do. You're always going to be either 1, 2, 3, or 4. There's no other way for you to react to this. So we've covered the complete set of behavior in this variable. In the same way, we also can complete the characteristic behavior of variable Y here. And so this is basically what the response function is. It lists all the possible reactions of a variable to its parents. Okay. So now we're going to do a little bit more complicated stuff. This makes much more sense if you read it in your paper as well, but I'm still going to try to give you an intuitive explanation. So we have the observed probabilities B. So I show here PV of ZDY. So that's a joint probability statement. There's going to be 2 to the 3, so 8 different combinations of that. And that's our observed data here. So we can just write PV. That's what we know. You can go in the world, you can measure. On the other hand, with these response function variables here, so RZ, RD, and RY, we have a latent model. So that's a model where we model all possible behaviors of the patient to the doctor's prescription. But we have no idea what the probabilities are of these. So what we do is we set these equal. What we can just say is the observed data is equal to that model, and we use these indicator functions to figure out which state of the response functions correspond to which states in the observed functions. That can be quite finicky and complicated, and you can do it on pen and paper once, and then you'll see what it means. But all that matters now is that we have a formulation now to connect observed data with an unobserved latent model. And so here in this example, let's say we just have X and Y. Then we can just state the joint probability. So P of X and Y equals, and then we have again the joint probability here of Rx and Ry, and we sum over all possible states. And then these indicator functions make sure that each state is assigned to the right observed state in the reality. So once one of those guys is 0, the whole term is 0, and the whole thing turns to 0 for that specific combination of Rx and Ry. I know that saying that before doesn't do very well, but the story here is that you can take your observed model and you can infuse data and probability into your latent model. So a latent model becomes actually informed by real world data. The same way, we can also then characterize or describe a effect. So here TCE means total causal effect. In that case, you want to see what the intervention, the differences between x1 and x0. So if we change that from 0 to 1, we just take the difference here, and this is potential outcomes notation, between y when x is 1 and y when x is 0. And that would be our causal effect in this very, very simple model. We can just write that here as this summation minus this summation. You have to read the paper to fully understand this, but again, it's just about the conceptual description. So after we've done all this reformulating with response functions, and we've gained the ability to write a latent model and connect it with the observed model, we can actually now optimize it, because it turns out that this whole problem we just described is a linear problem, which means it's convex, which means that all local solutions are actually the global solution. So there's only one solution. And so it turns out that when we maximize the model, we get the upper bound, and when we minimize the model, we get the lower bound. So that's the good thing with convex problems. So what that looks like is that we specify a linear program. We say we want to minimize or maximize an objective of interest. So, for example, the effect of gene A knockout on a specific phenotype. And then we constrain the model here with these constraints. And specifically, what we have here is the matching of the data. So again, this would be the latent model. This would be the observed data. And then here we have the probability syntax. So we don't want to violate the rules of probability theory, which means we have to sum it all to 1 on the latent model. And we also have to ignore it. So effectively, this is just an intuitive explanation. But these constraints here all together, they're going to constrain here a space of possible solutions. And then when we optimize the space, this is would be high dimensional, but I just showed to you for 2 dimensions. When we optimize the space and we get the highest point, the lowest point, and that would be your lower bound. That's partial identification on an intuitive level. Okay, well, that sounds all great, but of course, there's no free lunch in statistics. There's always trade-offs, and the fact is that actually partial identification is a really, really hard problem, because I just shown it to you in binary, but if you crank up the whole system, you add more variables and you add more parameters, it's quickly going to come to a state that's impossible to compute anyway. So let's take a look at how it actually happens. So let's move beyond the IB model. That's the IB model here. And the response function variables have 2 ingredients. It's a formula you can show. But basically, the number of variables, so you saw RZ had 0 and 1 for the doctor, and RD had 0, 1, 2, 3 for the always takers, the always defiers, the compliers, and the defiers. The always takers and absence. And so what we're gonna do is we can actually use this formula to figure out how many states each of those variables is gonna have. So you take the domain, so that was all binary, so that's going to be 2, and then you take the domain from the incoming parents. So we're gonna keep in theoretical here, we're gonna try this straight away. So S here has no parents, which means that when its domain is binary, S is just gonna have 2 parameters. So that's 2. W here, again, has a domain of 2, and it has 1 parent that has a domain of 2. So it's 2 to the power of 2. A is the same story as well. There's only 1 parent coming in here in this graph. So this is a more complicated graph. And so again, we're going to have 2 to the power of 2. Now Y is much, much, much bigger. Because Y has not just 1 parent with a domain of 2, but 3 parents. So it's going to be the domain of Y, which is 0, 1, so 2 states, to the power of 2 times 2 times 2. And that's 256 states. And that's just a model for variables. But we're not done there yet because we need to multiply them. So this model alone here only has, 4 variables, but it has 8,200 parameters. Now with, modern linear programs, that's not a problem, but you can quickly see how things will become very problematic, if we increase the domain just of Y, or if we add another variable here. So that's really, really bad. Specifically, these response function variable spaces, they increase super exponentially. So, one model has maybe 1 variable, you add another one, and suddenly your computer stops running because it has taken all the RAM. It's literally this binding instead. So how do we deal with that? Well, let's take a look, at some solutions. It's maybe going to help us make this cool. So this is where this paper here comes in. And so in that paper, we introduced the causal marginal polytope, which is basically the idea of that we take this whole graph and we look at smaller parts of it at the same time. So we have 4 variables here. This would be kind of the worst causal graph you can see in the real world, which is that everything is connected and everything is confounded as well. So I haven't explained it, but these bidirected edges here with the dashed lines, these actually indicate confounding. So you can just imagine another latent variable here. And you see if there's a confounder and there's a confounder. There's a lot of confounders. It's really, really bad case. So this model here has 1 marginal. So 1 marginal would be here x1 to x4. So it has 4 variables. And if we were doing partial identification with this model, we would be looking at 32,000 parameters already. And so that is actually a very similar model. It's the same model as before. It just has 1 more edge here. And now we already went from 8,000 to 32,000 parameters. Okay, now that's where the causal marginal polytope becomes quite useful, because in this case here, we're going to look at marginals each with 3 variables. So if you're looking at all combinations of zoomed in views of this model, and you were looking at combinations that have 3 variables, you would come up with these 4 submodels in a sense. So we took this model here, and we looked at 4 different versions of it, where we basically summarize 1 variable into the other ones. For example, here, there's no x4 because we summarize it into the other variables. And so each of these marginals here now becomes a dedicated partial identification model. And each of those here only has 128 parameters. And then we have 4 of those. So this model only has 512, which is radically less than these. Now, of course, there's nothing for free, because if you summarize, x4, for example, into this other one here, and so you don't have it anymore part as the model, you're losing information efficiency. So what you're going to have is that the bounds are going to be more loose, and more loose bounds means that they're not going to be as informative, which is not that cool, right? So what do we do now? Well, we're going to add constraints. So constraints through the space, reducing the space, making the solution space smaller. And if the solution space is smaller, our bounds are going to be more tight as well. So the first one we get for free. And the first one is called the overlap constraint. So for example, if you have 2 marginals here, they still share x1 and x2. And what we can do is we can actually set them equal. So if we have the marginal here, x1, x2, and x3, and we sum over x3, then that marginal is going to reduce to P of x1 and x2 with x3 reduced into that joint probability. And we can do the same thing here. So x1, x2, and x4. If you sum over x4, you're just going to have P of x1, x2. Well, we can always say P of x1, x2 in the first marginal equals P of x1, x2 in the second marginal. So that's the overlap of information. So we can share information between the marginals. And you can do that with all of them together. And so that way we can reduce the space and therefore also get a bit more tight bounds. The second, so again, back to the linear program, minimize or maximize the objective according to these constraints. And now we're just gonna attach that extra constraint here, or however you many overlaps you find. The next one is called expert knowledge. So we have these bidirected and these directed edges here. So again, these are bidirected edges. So you see two arrows here, and they indicate confounding. And then we have these direct edges here. They indicate, direct effects. So x1 would be directly influencing x4. So with expert knowledge, we can reduce the influence of these edges. So we can argue, for example, that x1 to x4 in this marginal here is actually a very weak relationship. And so by stating that it is a weak relationship with a certain number, of accuracy or error rate, we can again reduce the space of solutions. So this is a little bit more complicated to write mathematically. Here's just the formula from the paper. But long story short, we again add more constraints, and again we can reduce the space. So you see here that we have an absolute value between this statement here minus this statement here, and then we have this parameter here. So this is the subject parameter. It's like a knob you turn on the oven, from 0 to 1. And if you turn it away all the way to 0, so you see that here, if that is 0, that means that this expression here also needs to be 0, which means that these expressions here needs to be equal. And you kind of read in the paper why that is useful. Okay. Right. So welcome to the causal marginal polytope. How does it look like in an example when we can simulate some data and see how these graphs all work together? Here, we're going to look at, again, the four-variable graph, and we're going to just constrain this directed edge here, and then the bidirected edge up there. We're going to give these data points to the model. So this is the observational regime, which means we're not intervening at all. This one here would be a single intervention regime. So I haven't introduced that much, but basically, if I say do x2, it means that I set x2 to a certain value, which means that all of these arrows here are cut, and basically it's in an intervention stage. So this is similar to intervening on a system, and you can do the same thing here. So the reason we do that is so that we can show that when the model has the data on certain causal effects, it actually has identification as well. So this one here, this plot shows all the possible causal effects in the model. There's only actually 18 in this model, but this is all possible causal effects. And so we see here, for example, that with do x3, we have given the model already the answer to this causal effect. That is why the lower bound and the upper bound are both the same. That makes sense, right? So if the lower bound and the upper bound are pointing to the same number, that means that we've actually identified the causal effect. And you see that here in the middle cluster as well. These are all the causal effects that the model can already infer from this data. The other effects around here, you can see they're not just from 0 to 1, but we can see that they're also constrained further along here. So that is quite useful. For example, this range is much smaller than this one here. So depending on what your problem is, you find some causal effects have already very good bounds. But that's not enough. We want more. So with the overlap constraint, we can show here that when we take this unconstrained model here, so that would be without the constraint A, without the constraint B. If we then add the constraint A, we can actually constrain two effects of interest. So P of x equals 1, if we intervene on x equals 0, x1 equals 0, then we see actually that when the overlap constraint is enabled, here the right side hand, we almost halve the bound around that. So that's the information sharing happening between the marginals. Now, a separate constraint here would be the weak directed edge. So if we go back here, that would be the red line, the red edge down here from x1 to x4. If we say, you know, if we keep decreasing that epsilon here, that is the weakness of the edge, we see here that the bounds are getting shorter and shorter as well. But there's something very important happening here, which is quite important for coarse inference as well, which is that we have these x's here that indicate invalid bounds. That's when our bounds went too tight and excluded the true causal effect. And so that's not good, right? So if you were talking to a health specialist and you were, you know, putting an epsilon value into the model, and you actually excluding the true causal effect, then that can have, you know, bad consequences, right? So here in the simulation, we have access to the truth, and we can see here that the true effect gets excluded here, and these bound ranges here are actually wrong. So that's unfortunately something we can actually verify, just like confounding in the real world, but at least in the simulation, we can see how it behaves and, you know, inform the expert that gives us that knowledge, that their knowledge is quite important and needs to be actively stated. And then finally, the weak bidirected edge constraint, we can see as well here that, you know, moving the epsilon to smaller and smaller values gives us tightening of the constraints. But what we see here then is that around 0.12, we actually get an infeasible model. And so an infeasible linear program implies that the data that we gave to the model says this model doesn't make any sense. What I see in the data is not what you're telling me in the epsilon value. So I'm infeasible, there's no solution. And that way we can actually falsify at least weak bidirected edge choices. So 0.06, for example, the data would say, nah, this doesn't make any sense. This is clearly wrong. So that is again a constraint where data can actually be useful to falsify that. So expert knowledge practically is infused then with the middle constraint here. Okay. So that was the causal marginal polytope. And let's review that again. So number one, if we do not want to assume structural knowledge, then we can still try to get some bounds on the causal effect. And that would be partial identification. But unfortunately, the world isn't that pretty, and there is no free lunch, which means that partial identification, as always, despite being so nice, is a really hard method. And there have to be trade-offs to do all of these things. Okay, so there are some alternatives to these methods. Well, they're harder to explain, but I'm gonna show you an intuitive explanation here. If you haven't listened to the talk so far, then you should definitely listen now, because this one is quite useful to understand causal inference itself as well, and it is part of newer research in the area. And this simple example actually very beautifully showcases the whole idea of partial identification. Okay, so what's the idea really behind partial identification? Again, here we'll just take the instrumental variable setting. So we have the instrument or the doctor that makes a prescription, we have the treatment, and then we have the outcome. So that could be aspirin, and then you had it on the next day. This table here would indicate all possible reactions of A to its parents. So if A had two inputs, we can see that C and U, and then all possible combinations of the inputs would produce all these outputs of A. So this is how structural, graphs work. They always have parents that provide values. The child listens to the parents in a sense, and then based on whatever function the child has, produces an output based on the inputs. On the right side here, we have the same thing for B. B also has two parents, namely U and A, so U and A here. But we're looking at two different functions for B. So we have F1B and F2B. And so these two functions indicate basically two different ideas of how the world might be. We can't exclude one or the other. We might have knowledge of them. It's in a sense two different models about the causal process. In this case, it's actually not too different we see that when U is 0 and A is 1, then F2B is still going to produce a 0 here. So in F2B, B here will only ever be 1 if both U and A are 1. So it's two different models. We'll see very shortly why that's relevant. So for this explanation, we're going to say that P, the probability of U equals 1 is P. So by probability theory, P of U equals 0 is 1 minus P. So very simple. And so the first model here with F1B implies that the probability of B equals 1 given A equals 1, so dimension of A equals 1, is 1. So let's see that here. So probability of B equals 1, well, there's two options here. And A is 1 here as well. So in 100% of the cases, this statement is true, which means it's 1. So probability of 1. Now, probability of B equals 1, given do A equals 0. So let's take a look at the table here. So we have that one here. And in fact, for whenever B is 1, there's no state of A where it's 0. So the probability of that is going to be 0. Well, that's very easy. So the cause and effect, which is the difference of this probability statement and this one here, is going to be 1 minus 0, which is 1. That is the first model. Let's take a look at the second model, a second idea, a second assumption of how the world looks like. B equals the probability of B equals 1 given A equals 1. Let's take a look at that. Well, B is only ever 1 here in model 2. And the probability of A, so A is 1 here too, and then U is 1 here too. Well, we've defined P of U equals 1 is P. So this is going to be that P. It's that probability of U being 1. So that's different here, right? We see again, we have the same story here. So that's going to be 0. And then the average false effect in the second model is going to be P minus 0, which is P. So we have two models that we're looking at in this instrumental variable model setting. And to produce two different cause effects, well, what we now do is we just say the bounds are the lowest cause effect and the highest cause effect. So the bound in this model, in this setting where we have two models, is simply going to be from P to 1. So P is just a parameter of the model. You can set it as simulation or maybe estimate, or maybe not in this case. This is a really central idea. And why is it central? Well, we can use it to do a bit more complicated stuff. So what we can do is we can specify a cause effect of interest. I'm not going to explain all the details here because you can see it in this paper. But what's more important in this approximate formulation of partial identification is a distance function here. And so in this distance function, we're going to first look at a class of all possible models. That could be thousands, that could be tens of thousands. Then we're going to reject all the models that disagree with the data. So we can do that with a distance function here. You know, the same way when there was infeasibility in the other problem, the same way we can, turn this epsilon smaller and smaller, and we can check all the models that don't fit with the data. Let's say we're left with 100 models. Of those 100 models, we can just now calculate the effect of interest. And then we have 100 of those. And the minimum and the maximum of that is going to be our bounds. So this is how we can actually do approximate partial identification. And here's some examples there. So there's two formulations. One is with a GAN, one is with a augmented Lagrangian. And we see here that especially with the augmented Lagrangian, with a very smooth bound here on the true cause effect, and then another smooth bound here as well. So that's an alternative, which you can read up here, but that's obviously much more complicated than the cause and margin. Okay, so instead of 45 minutes, we're coming to the end here. So really my core message for you today is that causal modeling is actually not about identification. So I kind of like teased you there and I said it's all about identification, and the story is actually it's not. So we're moving into a stage of where partial identification is going to be also maybe a quite crucial part of the toolset. And so here are some quotes from my supervisor. So he would say, don't say, I can't provide a unique solution from your assumptions, I'm going to go home, no answer. Instead, you want to say, these are all the solutions compatible with my assumptions. It's a very different perspective on data science in a sense. So instead of having like two binary responses of, well, either you take my strong assumptions or you get no answer, there's actually a middle space, and that middle space would be partial identification. And then there's no academic talk about a mean. So how it started, the core question of causal inference is identifiability. Well, actually how it's going, make the best out of the variables. Right, so that was my marathon today. And so we can do questions, answers, depending on how many questions are. We might take the questions first and then answer them one by one. We'll see that. Questions, discussion, feedback. Also have 4 more slides. 14 more slides. You want to take a look at specific things. Oh, and yeah, there's a web page where you can learn more about questions. Yeah, that's it. Thank you so much.
I can start. Thank you for the talk. I didn't understand half of it, but it's okay. I'm an applied researcher, so I'm thinking about this as an applied researcher. My thinking about it is how can I apply this method, this new method in my research practice. So let's try to kind of to be guided by an example. Let's take this classic question, the causal effect of education on earnings, right? Explored so many times. We can't identify it directly. There are so many confounders. We don't know the confounders, motivation, cognitive ability, non-cognitive skills. We can't measure them. So we have a classic situation with confounders. We can't do a perfect experiment for kind of practical reasons. In theory, ideally, there are no ideal experiments, but if we could do an experiment, we wouldn't need any strong assumption. There are always assumptions, right?
Yeah.
But we can do full identification. Then what we can do, we can use, and that's been done in labor economics, we can try to find a natural experiment, the change in compulsory schooling laws, right? And then we specify an instrumental variable model, and we can achieve some identification. It's going to be local, late, local average effect. We can, but that's better than nothing, right?
Right, better than nothing.
Okay, better than nothing. Now we have this partial identification, right? I've got 2 things measured: education, income, and I know that there are confounders. Can you tell me how I can measure partially identify my causal effects and to come up with those bounds for my causal effects?
So I think the initial formulation from the PO guys in 1990, that was also in the IB setting. So if I was going to recommend, if I wanted to show someone how can you do this, I would start with a problem where you actually have an IB setting. So it sounds like you might have one or 2 of those cases. And so in that case, you can actually download, I think it's even an R package maybe, where you can just provide the data and it will give you the bounds for the IB model. So these R packages exist. The things I've shown you today are probably going to take still maybe 3 to 5 years before they become actually usable, like user-friendly. Like the causal margin prototype, in my opinion, even though it's my own research, I think it's entirely not user-friendly. But then again, as you say, it's better than nothing. But I just think it will take 3 to 5 years at least before this all has become more usable, more accessible. But what's accessible today is in these bounds on instrumental variable models. So if you go to all the initial papers, they're also listed. Also marginal polynomial paper in the introduction. You'll find the paper, for example, by Pearl, and there you can just download the software. Can't find that. I can help you find it as well. But there could be the idea is that would be an additional part to your analysis. So instead of going from nothing to here's at least something, it would also be, and then partial identification, we have a model that has weaker assumptions, and here the bounds to that. So the problem is that the less information you have, or the harder the problem is, the wider the bounds are going to be. But the thing is, I personally think that knowing nothing compared to knowing the bounds is still better than nothing. And so so long story short, if you have an IB problem, we could do the math on the board today in 10 minutes to get you some bounds. If you have a bigger problem, if you have bigger causal graphs, that's going to be quite a bit harder. a little bit ahead of its time. Not that we're super smart. It's just like causal inference suffers a bit from fatigue because of all the different opinions. That is, for example, potential outcomes, which is a little bit in graphical models. So everyone's using a different language to explain the same thing. And so that is why these methods take some time to actually become useful. Yeah.
I'm trying to get my head around the bound range.
Yeah.
And at what point does the bound become useful to a practitioner? I mean, it's semi-related to the last question. So as I'm imagining it, the lowest possible bound, the lower bound is -1, the highest possible upper bound is 1. And then at what point are you narrowing down the space enough that it becomes useful to someone to make a decision?
Yes, so I think the first observation you're going to make is that when the bounds, it's a very good question. Thank you for that. So the first thing that's going to happen is that when you bounce, if one of them is negative and the other one is positive, that means you can actually decide whether the cause effect is negative or positive, right? Because it could be, let's say if that was -0.1, then what these bounds would say is that your true causal effect is somewhere between -0.1 and 0.4. So that means it could be negative. So it means that drug could be hurting patients, but it could also be that it's actually hurting patients, it's helping patients quite a lot. And that is an expression of your data. There's now no gimmicks, no tricks you can do. That is just, it's nature in your face in a sense. Like there's nothing you can do about it. What you can do, for example, classically, is something called the monotonicity assumption. So that's often used in epidemiology, where you assume that, you can't ever hurt a patient with a certain drug. So we can actually see that nicely here. With monotonicity, you actually exclude option 3. So monotonicity means that you can actually never get worse. So if we assume that there's a drug, that taking the drug actually never would make someone feel worse. It's a common and popular assumption because it makes your analysis a bit easier. And so if you reduce the space of that response function variable from 4 options to 3 options, you reduce the space of the solutions, and your bounds are definitely going to get more tight. So that is something you would usually want to do in an analysis. You would say, here's partial identification, here are the bounds. Step 2, here are the bounds with monotonicity. How different does it look like? And so that way they can become useful. So for me personally, the first stop you're going to have for useful bounds here, the first useful stop is when you actually know the direction of the cause effect. That is already really powerful. I think Pearl has a paper where he calculates the bounds, and they don't include 0. So that's what they say. If the bounds don't include 0, that means the direction is clear. Either it's like negative or positive. And then to tighten the bounds, as I said, you can then use assumptions such as monotonicity and constrain the space further. And that's actually as far as it gets of usefulness to the practitioner. So these are the tricks you can, not tricks, these are the decisions you make as an analyst to deal with the bounds and justify the bounds. And then the data just gives you the bounds. How's the usefulness? Well, if you need answers in the range of 0.001, bounds is not the thing. If you just need the direction of the causal effect, positive and negative, bounds can be quite attractive, because if you get bounds that don't include 0 with weak assumptions, that's going to be a much better, much easier thing to explain and justify than no unmeasured compound. And so that is kind of where partial identification comes. It's a very central question, and there's actually not much work about figuring out the range of the bounds beforehand. So often you just plug in data and you get bounds, and you're like, easy problem, good bounds, bad problem, not so nice bounds. You can of course make segregations about that.
Do I understand it's correctly that those bounds shouldn't be confused with confidence intervals?
Yes, very good
Although
point.
they do look like confidence intervals.
Absolutely.
Each of those bounds would come with some measure of statistical uncertainty.
Yeah, excellent. Yeah.
So we have this bound interval and 2 more confidence intervals for the.
Yeah, absolutely right. So Actually, I always mention that, but I forgot it today. But it's absolutely correct. So let's say if you go from -1 to 1, and you have 0 here, then if you have these bounds here, so let's say this range, this is not a confidence interval. Absolutely not. Never think about it that way. Confidence interval are about random variability, about sampling and so forth. Which means that if you calculate your lower and upper bound, what you actually get is that for this lower bound here, that lower bound itself is going to have a constant confidence interval, and that upper bound itself is also going to have a confidence interval. Very important point. So I hope you learned something, but I hope you didn't learn something wrong. So this is not about confidence intervals. This is about bounds. And so these bounds, what they really mean is that the true causal effect is somewhere in between here. It could be right here, it could be right here, it could be right in the middle, or anywhere. But it's not a confidence interval. Because in a confidence interval, you choose let's say the alpha, and then you can choose how big you want the interval. With bounds, you have absolute guarantee that the true causal effect is never going to be lower than the lower bound, except maybe for a little bit of variation on the sample. But that's something I should put this one. Okay, I think
There might be some questions online, maybe.
Oh yeah, the chat.
That's just me.
Oh, okay.
Thank you.
So yeah, I think these 3 were actually really good questions. So yeah, if you want to start with it, just send me an email. I'll get you the paper for the IB model. It's very nice to start and to understand. And then the usefulness, well, if they don't include 0, it's pretty good, but we're usually constrained by the data. And then you can assume monotonicity that makes a nice additional analysis, but we would have to justify it. And then the third point, it's not confidence interval. These bounds are strict, they are tight, they are sharp, meaning that the true effect will never be lower. Whereas in confidence interval, you could choose still or you could do. Okay. Well, that was great. We're just about an hour now. There's one question. Good. Thank you.
Well, thank you very much, Jacob. There is tea and coffee, I promise this time, just outside the room. So please, you can stay around for a little bit longer.
Absolutely.
And yeah, thank you very much. And yeah, keep an eye on the IDSAI Seminar Series. It's on our website. Our next seminar is by Alexi, Professor Alexi, and I think we're back in this room. But anyway, yeah.